Okay, so we're going to start with a review of finding a domain of a function. So if you'll recall, there were two things that gave me problems with the domain being all real numbers. That's if we divide by zero or if we take the square root of something that is negative. Now, this chapter, we're going to be focusing on rational functions, which are all functions that have a fraction in them. So that first thing, the first problem, having a zero denominator, is what could really trip me up in this chapter. All right, but we're also going to take it a step further. We're going to see what it means that the domain cannot include something. So like in example A here, we're given the function r of x equals 2x squared minus 4 over x plus 5. And we're asked to find the domain. Okay, well again, remember, the thing that could give me a problem with the domain is if the denominator is 0, because we cannot divide by 0. So here I would say the denominator cannot be 5. Whoops, sorry. The denominator cannot be 0. And then solving that, I find x cannot be negative 5. Right, subtracting 5 from both sides. So you'll see that here they say that the domain is all x's such that x cannot be negative 5. Okay, the next one, x squared minus 4 is in the denominator. So I would say that cannot be equal to 0. Move the 4 over. That says x squared cannot be 4. We take a square root. X cannot be plus or minus 2. Very good. Remember, when we choose to take a square root, we must always take into account the plus or the minus possibility. All right?
Do you have to write it in like two separate things like that, or can we just put that?
I'm good if you just write x cannot be plus or minus 2. You see their answer, they separated it. They said it's all x's such that x is not negative 2 and x is not 2. If you wrote it as 1, that's fine with me. Okay? The next one, x to the third over x squared plus 1. Okay, so again, I would say the denominator cannot be equal to 0. I move the 1 over, it becomes negative. So it says x squared cannot be negative 1. Now watch this. Square root, square root. What do I have now? I've got x cannot be equal to a negative underneath the radical. So what's that going to be? That's going to be an imaginary number, right? Okay. In our graphs, we're talking about domain, which is, think about graphically. Do we ever graph imaginary numbers? No. So far, the only thing we've ever graphed in is the real number system. So if x cannot be something that's imaginary, well then I don't have to exclude anything. So again, you'll see they say the domain is all real numbers, right? Because something imaginary is the only thing that gives me a problem. Okay, look at the next rational function. I've got a 3 in the denominator. So when can 3 be 0? Okay, but it's not an equation, right? So what's always in the denominator? 3. Can that ever become 0? No. Okay, it's always a 3. So this is also the set of all real numbers because I can't make that be 0. Okay, and the last one here, I've got this rational function that says x squared minus 1 over x minus 1. Okay, now I'm going to say the denominator cannot be 0. So that says x cannot be 1. Okay, so again, the domain is all x's such that x does not equal 1. Everybody remember how to do this? Finding domains. Now, very quickly before we move to the next page, the next set of problems, let's look at example B, which was 1 over x squared minus 4. I could factor x squared minus 4 down, right? I could factor that to be x plus 2 times x minus 2, right? Now, are there any common factors between the numerator and denominator that I can cancel out? There's not, okay? So this is what that tells me, that there are two problems with my domain. They are at negative 2 and 2, and since nothing cancels, I know that these are vertical asymptotes, okay? And we'll talk a little bit more about what that is in just a second. But you should have heard me say that once or twice in class so far. All right? But now, look at this bottom example. X squared minus 1, I can factor that. That gives me what? X plus 1. Let's don't use green, Cody. That gives me x plus 1 times x minus 1 all over x minus 1.
So it's just gonna be x plus 1.
Now there's a common factor here, right? But now I still am not allowed to plug in 1, but because it cancels, that means that it's not a vertical asymptote, but it's what we call a hole, okay? And we'll look at what that is in more detail in just a second. Here we go. We are given 4 rational functions, and in each one, I'm told to find any vertical asymptotes, okay? So let's talk first graphically. What is a vertical asymptote? All right? If you'll look there in your book at the top of page 195, and I am fixing to get that picture up here on the projector as well. So there it is. Okay, what a vertical asymptote is, it is a vertical line straight up and down that my graph cannot cross. It cannot touch it, cannot cross it. Okay? So when I look at this vertical asymptote here, you'll see in this example, the graph gets lower and lower and gets closer to it, but never crosses it here. And then from this direction, it comes in super high, and then it starts to level off, right? All right. In this one, they both go in the same direction, right? They're both going up. But this here is a vertical asymptote that the graph cannot cross, all right? And so where do those vertical asymptotes happen at? All right. Well, let's first look at the first function. It says x over x minus 4. This is what you're always going to do to find vertical asymptotes. First, is that factored down into its lowest form?
No.
Can I factor the numerator? No. Can I factor the denominator? Yes. What is that factor to be?
X plus 2, x minus 2.
That's x plus 2 times x minus 2. Now, do I have any common factors? Anything that I can cross out, simplify? I do not. Okay, so that means there are not any holes. So that means where the denominator is undefined, where the denominator goes to 0, those are going to be vertical asymptotes. So I have vertical asymptotes where x plus 2 equals 0 and where x minus 2 equals 0. So at x equals negative 2 and x equals positive 2, I have vertical asymptotes. So my answer here would be at negative 2 and at positive 2. Okay, so again, thinking about that graphically, that means I'm just going to go to where x is negative 2, I'm going to put a vertical line. Then we're going to where x is positive 2, I'm going to put a vertical line. All right, and the graph cannot cross those vertical asymptotes. All right, that's what's going to happen. Now, we'll fill in the rest of it later. We're just getting pieces of it at the moment. Okay, let's look at the next one. I'm given the function f of x equals x plus 3 over x minus 1. I'm asked to find any vertical asymptotes. So first, can I factor the numerator? No. Can I factor the denominator? No. Is there anything I can cancel out as a common factor? No. So where are the vertical asymptotes?
Where x?
Where the denominator equals 0, which is at 1. So for this one, there is a vertical asymptote at x equals 1. I understand what that means graphically. I'm not going to do that for every one of these. Okay, look at example C. I'm given h of x equals x squared over x squared plus 1. First, can I factor it? X squared plus 1. Can I factor that? No. The denominator, x squared plus 1. Can I factor? I think I said that for the numerator, didn't I? I'm getting carried away. The numerator is x squared. It cannot be factored. The denominator is x squared plus 1. Can I factor that? It's not factorable either, okay? The last class, they said, is that not a sum of perfect squares?
No.
And I said, yeah, it is, but tell me how that factors. All right, we can't factor a sum of perfect squares. So this is as simplified as it gets. So that means there are no holes, and all the vertical asymptotes will happen when the denominator is equal to 0. So I'm going to set the denominator equal to 0 and solve. So where x squared equals -1, okay, then I'm going to take a square root of both sides.
Well, X is a imaginary number.
Okay, so again, I'm taking the square root of something that's negative, so it's imaginary numbers again. When I graph, am I dealing with imaginary numbers? No, we are not. Okay? So, where are the vertical asymptotes? Here, there are none. The only vertical asymptotes would happen now we look at D. Okay, so first I'm going to see, can I factor anything on D? The numerator, yes, that is a difference of perfect squares. So what does that factor to be?
X plus 3, X minus 3.
Very good. And then the denominator, can I factor that?
Yes.
You can. You can. So if you are not good at factoring, how would we factor that trinomial? We would do the A times C method. So you go ahead, work that out. See if you can figure out what it factors to be. Okay, so we found the denominator is x minus 3 times x plus 7. Now looking, do I have any common factors between the numerator and the denominator?
Yes, X minus 3.
I do. They both have an x minus 3. Okay, so since that crosses out, there's going to be a hole that happens there. And we'll talk about that again later. But for now, we're just finding the asymptotes. So the only place that an asymptote would occur is for this second factor, x plus 7, where it is equal to 0. So I would say, well, x plus 7 equals 0. That'll be when x is -7. So there is a vertical asymptote here at x equals -7. Okay, so we just got done talking about vertical asymptotes. Now, my graph can never, ever, never, never, ever, never, ever, never, ever, never, ever, never, ever cross a vertical asymptote. Never, ever. Did I stress that enough? Okay, so it's never going to cross a vertical asymptote. But the next thing we're fixing to talk about are horizontal or oblique asymptotes. Okay? Now these asymptotes tell what the graph does as my x gets really big or my x gets really small. So like to positive infinity and to negative infinity. Boy, that handwriting's bad. Horizontal or oblique asymptotes. Now, I'm going to say 90% of the time, and I just made that number up, 90% of the time, our graphs are not going to cross horizontal or oblique asymptotes. Okay? The majority of the problems we're going to look at, it's not going to cross them. But it can. Okay? Your graph is allowed to cross these. Your graph can never cross a vertical asymptote, but it can cross a horizontal or oblique asymptote. But it normally doesn't. Okay? So just make sure we understand that now. Now to learn about how we're going to find out which one we have, we'll look at that in just a second. But again, for every one of our examples, we're only going to have one or the other. We're going to have a horizontal or an oblique asymptote. We're never going to have both. Okay, now a quick review before we talk about how to find horizontal or oblique asymptotes. Let's talk about finding powers of polynomial functions. So say I had the function f of x equals x to the third minus 2x to the second plus 11x minus 3. And I ask you, what is the power of this function? You would tell me it is... Does anyone remember how to find powers of functions? Okay. The power of this function is 3. It's always the greatest exponent. Okay? That represents the power of the function. Now, or the degree. I don't know why I said power. I meant degree. I kept saying power. The degree of the function is 3. All right? Let's look at another one. If f of x equaled 11x to the 5th minus 7x to the 7th plus 18x minus 2, the degree of this function would be 7. Is everybody good with finding degrees? Okay, what about this? If I had f of x equals 7x, the degree of that function is 1. And then if I had f of x equals 11, the degree of that function is 0. Okay? It's like it has an x to the 0 power at the end. Because what is anything to the 0 power? Nope, incorrect. If I raise something to the 0 power, it is 1. It is 1. Okay? Okay, so we're going to now look at horizontal and oblique asymptotes. All right, we talked about that just a second ago. Now again, our graph can cross these, but it normally doesn't. Right, and this is how you know which kind of asymptotes you have, and I can tell you how you have to find it. All right, so we just did a quick review about powers. This is why. Say that I have f of x is equal to some rational function. So there's a power, there's a degree of the numerator, and there's a degree of the denominator. Okay? So let's say that the denominator has a larger degree, has a greater degree. So I'm going to put the numerator is a smaller degree than the denominator. Okay, when this is the case, when the numerator has a larger degree than when the denominator has a larger degree than the numerator, we have a horizontal asymptote. And it occurs at y equals 0, which is the x-axis, right? So an example, if I had f of x was equal to 3x squared minus 7x plus 11 over x to the third, and I ask you, does this have a horizontal or an oblique asymptote? You would say it is horizontal because the denominator has a greater power than the numerator. So you would say horizontal. And I automatically know it's at y equals 0. Okay, that's the easiest case. Whenever the degree of the numerator is smaller, that's the easiest case. Okay, so now what could happen? I said that the numerator could be smaller than the denominator, the degree. Okay, what if the degrees are equal? Okay, so the next example is, say f of x equals, I have equal degrees in the numerator and the denominator. So say it's an x to the third over an x to the third. Okay? When that happens, it's going to be a horizontal asymptote. And it occurs at y equals, nope, it's going to be the leading coefficient of the numerator, I can't spell, leading coefficient of the numerator over the leading coefficient of the denominator. Y'all can write that better than I did. You heard me say it. Leading coefficient of the numerator over the leading coefficient of the denominator. So let's look at an example very quickly. If I had f of x equals negative 2x to the fourth minus 7x to the third plus 11 over 5x to the fourth minus 8x to the second plus x. Okay? And I ask you, does this have a horizontal or an oblique asymptote? Okay, what's the degree of the numerator? It's 4. What's the degree of the denominator? It's 4. So since they're equal, I would say it's going to be horizontal. And it's going to happen at y equals
negative 2 over 5.
-2 over 5. Absolutely. So there's a horizontal asymptote at y equals negative 2/5. Now let's look at a different example when I have equal degrees. So what if I had the function f of x equals 7x to the third plus 2x to the fourth minus 1 over x to the fourth plus 3x squared minus 7x. Okay? What's the degree of the numerator? 4. What's the degree of the denominator? 4. So since the degrees are equal, this is going to be a horizontal asymptote. And it's going to occur at y equals, what's the leading coefficient of the numerator?
7.
Okay? The leading coefficient is the coefficient of the term with the highest degree.
Okay, 2.
So it's 2, okay?
Over 1.
If we have to rearrange it to see that, we can. But that's just the way that I like to explain it, as the leading coefficient. So you know it's the one with the highest degree. And then what is the leading coefficient of the denominator? 1. So this is a horizontal asymptote at y equals 1. I mean y equals 2. My fault.
Oh, you looked at me.
Been a day.
Okay, and then the last case that we have for identifying oblique or horizontal asymptotes. Okay, so the two examples we've looked at so far have both been horizontal asymptotes. So what do you think this last one's going to be? It's going to be oblique, all right? And this is the case when that happens. If I have a function is equal to, okay, say that the numerator is equal to some degree, all right? The degree of that polynomial is something. And then let's say that the denominator is 1 less than that degree. All right, and that's important. It has to be 1 smaller than it. Okay? If it's more than 1 smaller than it, then this doesn't work. But if it's 1 less than the degree of the numerator, then I'm going to have an oblique asymptote. And to find it, I'm going to have to do long division. Okay, so let's look at an example here. Say I have the function h of x equals 3x to the fourth minus x squared all over x to the third minus x squared plus 1. And I'm asked to find the horizontal or oblique asymptotes. So first I'm going to look at the degrees. The degree of the numerator is 4. The degree of the denominator is 3. It's 1 less than the degree of the numerator. So that means this is going to be an oblique asymptote, which just means it's some slanted line, right? It's a line with slope. It's not horizontal. It's not vertical. It's somewhere in between those, all right? And to find where it occurs, we are going to do long division. So let's do a quick review first of how division works. So let's do, what is 63 divided by 3? Okay. Nope, no calculator. We're going to do division up here. So now, we say, I've got a 3 and I want it to be a 6. How can I get from a 3 to a 6?
Times 2.
We multiply by 2. So then 2 times 3 is 6. And then we do what? We subtract. We add that subtraction on our own because that's how division works. Don't forget that because that's what you're going to have to do for long division. And then once we get that as a remainder of 0, we bring the next term down. Then we say 3 goes into 3 one time. Then same thing. 1 times 3 is 3. And then we have to subtract those. And when we do, we get a remainder of 0. Okay? So that was just a quick reminder. I wanted us to see that we subtract those when we do our division. And that's going to also be true for long division. So first, the number in the numerator goes inside your division box. Except for last year, who was our exchange student last year?
We had an exchange student.
Mm-hmm. She did theater.
Yeah, she did theater with me. What was her?
Clara, yeah. I tried to show her how to do this division. She learned theirs like this, and they actually put the big number out here, and they did the small one here. It was the craziest thing ever. Like, when we got to doing this part, I was like, She's like, I was like, show me how you do a regular division. And she did it like that. I was like, that's the craziest thing I've ever seen. So, for us here in America, we're all American, and we're going to do this a little differently. So, we put the numerator inside our division box. Now, listen very carefully. We must put the exponents in descending order, which means from biggest to smallest, and we cannot skip any exponents. You can't skip any of them. All right? So what is the greatest exponent that we have in the numerator? It's x to the 4th. So I've got 3x to the 4th. So next is my x to the 3rd term. What is it? There isn't one, right? So it's going to be plus 0x to the 3rd. We put it there as a placeholder. It will help you not mess up, I promise. Okay? Now the next term is x to the 2nd. Do I have that term? I do. So it's going to be minus an x squared. Okay, what about my x to the 1st term? Plus 0x. And then a constant term. 0. Okay? So that is what goes inside of your division box.
Wait, why did you not put a 0 in front of the x to the 2nd?
Because I have an x to the 2nd. It's -1. So you see this here that's underneath the division box. It's just 3x to the 4th minus x squared. Everything else is 0.
Okay.
And 3x to the 4th minus x squared.
Oh, okay.
They're the equivalent. They're the same thing. This is just a different form. Kind of like when we simplify fractions that are equivalent with different forms. Now we're going to do the same thing on the outside. What is the greatest degree that I have? X to the 3rd. So I'm going to write it down on the outside. So I've got an x to the 3rd. What's the next greatest degree? It would be the 2nd. I have that term as well. Next would be the 1st degree. Do I have a 1st degree term? I do not, so that's going to be plus 0x plus 1. Any questions so far? Now, our goal is to make my first term here eliminate the first term here. That's my goal. So I've got an x to the 3rd, and I want it to be 3x to the 4th. So how can I get from x to the 3rd to 3x to the 4th? I need to multiply by 3. I need to multiply by x. Okay, the 3 will give me the 3. And then x times x to the 3rd is x to the 4th. So this is 3x to the 4th. But now I have to multiply this 3x by everything else I have here. So what's 3x times negative x squared? That's going to be minus 3x to the third. What is 3x times 0x? That is 0x squared. And then what is 3x times 1?
3x.
Now, when I do this, I purposefully chose not to put a plus sign between my positive terms. But if I had a negative term, I did put the minus sign. Why did I do that? Because when we do division, we have to subtract, right? Just like we did on the last one. 63 divided by 3. We multiplied and then we subtracted because that's how division works. So guess what I have to do here? I have to subtract these terms, which means the 3x to the fourth is being subtracted. When I subtract a 3x to the third, that's minus a negative, so that becomes positive. My 0x to the second was positive, it becomes negative. My 3x was positive, it becomes negative. It changes the sign of every one of those terms. Okay? So now, we're going to go ahead and simplify this. 3x to the fourth minus 3x to the fourth is 0. 0x to the third plus 3x to the third is 3x to the third. Negative x squared minus 0x squared is minus x squared. 0x minus 3x is, and 0 has nothing with it, so I'm going to bring it down. Okay? Bring down your last term. Okay, and now we go through the same process again. Now my leading term is 3x to the third, and I want to make this x to the third eliminate that 3x to the third. So how can I make these two terms match? How can I get from x to the third to 3x to the third? I need to multiply by a positive 3. Now what is 3 times x to the third? That is 3x to the third. What is 3 times negative x squared?
Negative 3x.
Yep. What is 3 times 0x?
0x.
0x. And then what is 3 times 1? 3. Again, same thing. I do not put my positive signs. If you do and you go back and change them, that's fine. I was just always one that tried to save as many steps as possible. Okay, so now, in order to complete the division, I must subtract the bottom term from the top term, which means I'm going to change the sign of every one of these. Okay, when I do that, the first terms eliminate. If they don't eliminate, that means you've done it wrong. Okay? Because that was my goal, was to make it eliminate. So if it doesn't, you've messed up. Now the next thing, what is negative x squared plus 3x squared?
2x squared.
2x squared. What is negative 3x minus 0x?
Minus 3x.
And then 0 minus 3. Okay, now, this time it's a little different. I've got an x to the third, and I want to make it be x to the second. Okay? The only way I could do that would be if I divided by something over x, right? It'd have to be something over x. So when this happens, when this degree here is greater than the degree that is left, then all of the remaining part is the remainder. How about that? All of the remaining part down here is the remainder. Now, if we were doing long division to do long division, then this remainder would be important to us. And we'd have to bring it up here. But in the context of what we're doing, which is finding the equation of an oblique asymptote, the remainder is not important. Okay? All I'm going to focus on is this part up here. The part I got an answer for, which was 3x plus 3. So that means that my oblique asymptote is the line y equals 3x plus 3. Okay? Which just comes straight from your answer to your division problem. Okay, so looking at this one, if I'm asked to find the horizontal asymptotes, then I'm going to look at the degrees of the numerator and the denominator. Okay? So in this problem, what's the degree of the numerator?
2.
What's the degree of the denominator?
2.
So they are equal. So am I going to have a horizontal or an oblique asymptote? It's going to be horizontal. And where is it going to be at? It's going to be at y equals 2. How did you get that? Because we do the leading coefficient of the numerator divided by the leading coefficient of the denominator, which simplifies to be 2. Okay? Very good. Okay, and then here's the one last example of horizontal and oblique asymptotes. So again, we're looking at the degrees. What's the degree of my numerator? What's the degree of the denominator? 3. So the degree of the numerator is 2 more than the degree of the denominator. No. So that's not one of the cases we talked about, right? If the bottom is bigger, if the bottom has a bigger degree, then it's always at y equals 0. If they are of equal degrees, then it's horizontal at y equals the leading coefficients. If the numerator is of 1 degree greater than the denominator, then we do long division, and it's an oblique asymptote. But now the numerator is 2 degrees greater than the denominator. So when this happens, if I was asked to find the horizontal or oblique asymptotes, my answer would be none. There are none. Okay? The asymptote would actually be parabola shaped, which is going to have very little effect on what it looks like. And so we're not even going to bother graphing it at this point. Okay? So it's going to be none. None. Any questions about that? Okay, now let's look at a couple of problems and put all this together. So looking at this rational function, I'm going to put all of these things together. I'm going to identify any vertical asymptotes. I'm going to identify any holes in the graph. And I'm going to identify the horizontal or oblique asymptotes.
You're going to have both of them?
Okay, so first, identify the vertical asymptotes. So in order to find the vertical asymptotes or the holes, we need the equation, we need the rational function to be in a factored form. So look at this one. This one starts off factored. Do you see that? The denominator is already factored for me. So is the numerator. So are there any common factors that cancel out? No. So if nothing cancels, then that means there are no holes. Okay? Because the holes only happen where it cancels. Now, where do the vertical asymptotes happen? Where the denominator is equal to 0. So I'm going to solve both of these. I'm going to say, well, what happens when x plus 3 is 0?
It's -3.
And what happens when 4 minus x is 0? So this would be when x is -3, I have a problem. And when x is 4, I have a problem. So my vertical asymptotes are at x equals -3 and x equals 4. Those are the equations of the vertical lines, the vertical asymptotes. Okay? And in order to find vertical asymptotes and holes, we need this to be factored. And it already was. Now, to find the horizontal or oblique asymptotes, we need this thing not to be factored. Okay? We need it to be in its regular rational equation form. So I'm going to have to distribute the denominator. No.
I remember it. That's how I remember it.
Well, it's distribute. I want to distribute the denominator. So this would be 6 over, now distribute here. X times 4 is 4x. X times -x is -x squared. 3 times 4 is 12. 3 times negative x is minus 3x. So when I rearrange this, that's going to give me
Negative x squared plus x plus 4.
6 over negative x squared minus 3x and 4x is plus x plus 12. So now, when it's in this form, what's the degree of the numerator? 0. What's the degree of the denominator? 2. So when the degree of the denominator is greater than the degree of the numerator, it's always going to be a horizontal asymptote that happens at y equals 0. Okay, now we've got one more we're going to do. Now, looking at this one, it is not factored, right? It's already in the distributed form. So the first thing I'm going to do is factor it, because we need both forms of our rational functions. So looking at the numerator, will that factor x squared plus 6x plus 5? It will. And again, remember, if you're not good at factoring, you can use the a times c method to rewrite the middle term. But you could just look at that and see what that factors to be, hopefully, because the leading coefficient's 1. So that factors to be x plus 5 times x plus 1. Now the denominator is a little trickier because the leading coefficient is 2. So I'm going to do the a times c method. Okay? So I'm going to make a little side note. I'm going to do 2x squared plus 7x plus 5. A times c gives me 10. What multiplies to be 10? 1 and 10, 2 and 5. Which of those can I rewrite the middle term, 7x, with? That would be 2 and 5. Very good. So this gives me 2x squared plus 2x plus 5x plus 5. Okay, good. Now, I'm going to group the first two terms and the last two terms. What's the GCF of the first two terms? 2x. What's left in parentheses? X plus 1. What's the GCF of the last two terms? 5. What's left in parentheses? So that means the grouping worked because the parentheses match. And that's going to factor to be what's in front of the parentheses, 2x plus 5, times the matching parentheses, x plus 1. So now I have a factored form and I have a distributed form of my rational equation, which is great. So now let's first identify any vertical asymptotes or holes. Let's do that in blue here. Vertical asymptotes or holes. Okay, so I look, are there any common factors between the numerator and the denominator? There are. They both have an x plus 1. So that means that causes a hole in the graph. So where does the hole happen at? It happens when x is equal to negative 1. You set x plus 1 equal to 0. You solve it, which means there's a hole at negative 1. Okay, good. Now, is there anything left in the denominator that could give me a problem? There is. 2x plus 5 could be equal to 0. So that would cause a vertical asymptote. So I'm going to say 2x plus 5 equals 0. That says 2x equals negative 5, which gives me x equals negative 5 halves. So at x equals negative 5 halves, I'm going to have a vertical asymptote. All right? Any questions about those two? Okay. Then lastly, we're going to identify the horizontal / oblique asymptote. To do that, we look at the degree of the numerator and the denominator. The degree of the numerator is 2. The degree of the denominator is 2. 2. They are matching. So when they're equal, it is a horizontal asymptote at y equals 1/2. It's the leading coefficient divided by the leading coefficient. So that's 1/2, which is how I get y equals 1/2. Now tomorrow we'll go over how to graph these on a graph. All right? And we'll also be finding the x-intercepts and the y-intercepts to help us get shape to our graph. Okay, so for homework, we need to be doing page 200. We're going to do numbers 13, 19, 41, and 43. Now, I don't want you to do what the directions say. I want you to do what we did on those last two problems. I want you to find any vertical asymptotes or holes, and I want us to find any horizontal asymptotes.